We are Team 5 and we are happy to share our localization algorithm that we've worked on the past couple of weeks. Determining a robot's orientation and position in an environment in real time, known as localization, combined with mapping the environment, are two critical problems necessary to build an autonomous vehicle, as they provide the infrastructure to enact motion planning. Combined, these processes are known as simultaneous localization and mapping, or SLAM. For this lab, the goal is to implement localization through Monte Carlo localization or particle filtering, the first step in achieving SLAM. On a high level, Monte Carlo localization works by assessing the probabilities of having the measured exteroceptive LiDAR data at each particle on the map, starting with a random distribution of particles. The algorithm then starts sampling at locations with high probabilities, and as the robot moves, new LiDAR data will continue refining the map until the particles settle on the robot. A motion model represents the odometry of the robot, while a sensor model calculates the measurement likelihood. I will let Gongyi speak in detail about the motion model.
Thank you, Kevin. The principle behind the particle filter is to maintain a set of particles which each represents an estimate of the robot's pose, consisting of an xy location and an angle theta. We want to update each estimated pose when the car reports movement through an odometry reading. This data takes the form of a translation by dx and dy, followed by a rotation by d theta. The odometry dx and dy are in the poses frame, so we must first rotate it to the world frame using the theta of the original pose. As shown, the odometry gets applied to every particle in the set to give us a new set of particles. Now, simply applying the odometry to the particles will result in a buildup of noise from the odometry sensor in the car. Even a correct pose estimate will diverge from the ground truth eventually. The solution is to add artificial noise so that our set of particles will model the uncertainty in measurement. If enough noise is added, one of the particles should be close enough to the true pose, shown in black. Now, this set of particles will diverge really quickly, so Andy will talk about the sensor model, which will use observations to choose the most useful particles to keep.
Thanks, Gongi. So the purpose of the sensor model is to account for any uncertainty in our LiDAR measurements when the robot's trying to localize in a known map. When the model receives a list of particles, its goal is to determine the probability that the simulated LiDAR scan for a given particle matches up with our actual LiDAR measurement. This will help us choose later on which particles are the most likely to be the robot's actual location. Using ray tracing, we obtain simulated LiDAR scans for each of the particles being considered. Taking one LiDAR beam at a time, we can very quickly look up the probability of the real LiDAR beam existing given the ground truth beam in a table of conditional probabilities, which I will discuss how to determine next. Each conditional probability is calculated in 4 parts that are scaled and summed together in order to create a valid new probability distribution. Each individual distribution accounts for various types of measurements and noise, such as what happens at the short and long edges of the LiDAR's range. Here's a graph of all the resulting distributions. All of these probabilities are pre-calculated and stored in a lookup table, which allows for quick access later on without having to recalculate the conditional probability at each step. Now I'll hand it off to Andrea to talk about the integration of the particle filter.
Thank you, Andy. Now we will discuss integration. The last step is putting it all together, combining both the sensor model and motion model in order to estimate the robot's location in the world frame. We represent the localization of the robot by maintaining a set of samples randomly drawn from the probability density function provided by the sensor model, which are represented by particles in our case. We use particle filtering and estimation of Bayesian filtering as we update the beliefs of the robot positioning based on its previous pose, and then updating our probabilities of our particles accordingly in order to get an average pose. We apply the motion model to the set of sampled particles in order to undergo the prediction step, and then the sensor model to the same set of sampled particles to perform an update on beliefs. Both the sensor model and motion model are being called independently to update them and need to do so in a certain order. Since they're both applying changes to the same set of data, we need to ensure that there are locks implemented so as to make our functions thread safe and ensure a lack of concurrent access and modification. As Andy said, after performing both the prediction and update phases, we reweigh the probability and validity of each sample pose. The particle filter implemented is not a true Monte Carlo localization algorithm, but closer to a common filter. This is because we're assuming that the probabilities and post estimates given are from a Gaussian distribution, and therefore unimodal, so we obtain the post by getting the linear mean of the updated sensor model particles' x and y positions, and getting the angle by using mean of circular quantities. Despite this, our sensor model is able to accurately predict the pose of our car as shown in the video, where the particle array of all beliefs is shown centered around the car.
Just as Andrea explained, when we implemented our filter, we assumed linearity. But this common filter algorithm does not hold true for nonlinear transformations since the posterior is not guaranteed to be normally distributed. Imagine a global localization problem where we need not only to keep track of the robot's pose, but also to identify it. Representing the pose with a multinomial instead of a unimodal Gaussian is intuitive since we're guessing between a few possible locations. Applying a Monte Carlo filtering can solve that problem since it is much more general. However, a limitation of this algorithm is that it is much more computationally heavy to compute conditional probabilities via integration. The best improvement we can apply is an unscented common filter, which applies a deterministic sampling of very few points to represent a Gaussian pose distribution around the mean. Despite these areas for improvement, we successfully implemented a particle filter. This is fundamental when creating future motion planning, as we can accurately estimate the robot's location on a map. Thank you for the attention. Are there any questions?